All right, so you gave this practice 10.19 a try, so let's kind of go through it, see how you did. So we have a 2.2 kilogram hoop, 1.2 meters in diameter. It's rolling to the right without slipping on a horizontal floor at a steady 3 radians per second. How fast is the center moving? Okay, so since it is rolling without slipping, and I'm trying to find the velocity of the center of mass. So whenever you run into a situation where something is rolling without slipping, whenever this is the case, rolling without slipping, I know the center of mass velocity is equal to omega times r, where r is the radius that it is rolling on. And so for us, VCM is going to be our omega 3 times our radius 0.6. And so we end up with 1.8 meters per second is how fast it is rolling. Part B wants to know, what is the total kinetic energy of the hoop? Okay, so for part B, we're trying to find the total kinetic energy. Well, the total kinetic energy is a combination of our translational kinetic energy and our rotational kinetic energy. And so since this is both moving and rotating, it will have both types. So our total kinetic energy is going to be 1/2 mv squared for the translational plus 1/2 I omega squared for the rotational. Now they did tell me it was a hoop, so the moment of inertia for a hoop is mr squared. I'm also going to go ahead and relate the speed and the omega. So I'm going to divide the r over here. And so I can say that omega is equal to v over r. And so omega squared would be v squared over r squared. So my kinetic energy total is going to be 1/2 mv squared plus 1/2 times mr squared times v squared over r squared. And when I made this kind of substitution here, this v is that linear speed, that VCM we were talking about. So these two v's are the same. I do see that because it has a radius of r and it's rolling on that radius, those r's are going to cancel for me. So I have 1/2 mv squared plus 1/2 mv squared. So I end up with just mv squared, my two values of 2.2 times my speed, which was my 1.8 squared, will give me a total kinetic energy. Total kinetic, my goodness. Let's try that again. Total kinetic energy of 7.2 joules. Now, part C wants you to basically look at that diagram right below. So let's pull that up right now. And so we see in our diagram that if we look at just the translational part, we see that all of the points on the wheel have a linear velocity to the right. Now, if I look at only the rotational part, so spot in the middle isn't rotating, and the further I get to the edge, the faster those points are moving linearly. And so if I draw the linear velocity for any point on the rim, I see that they're all kind of going in a circle like that. So the top is moving to the right, the bottom is moving down to the left, the side is moving up or down, depending on which side you look at. And then when I add those two linear velocity vectors together, I get the vectors I see in that picture on the right there. And the key point to note here is at the bottom, the velocity is 0 relative to the road because it's rolling without slipping. And that's because it's moving to the right linearly, but rotationally it's moving to the left, and those two cancel each other out. So its net velocity there, or its relative velocity to the ground, is 0. And that is how you kind of answer that part C. There you go.